Alright, so chapter 3, numerical summaries of data, basically goes over ways that we can analyze our data numerically. In chapter 2, we looked at analyzing the data graphically, but this chapter, we're going to look at how we can look at the numbers and analyze the data numerically. Alright, so the first thing we want to talk about is the mean. Now, the mean is the average of your observations. Typically, people call it the average, but the technical name is the mean. The formula for the mean is given below. Basically, all you do is add up your observations and then divide it by however many observations you have. Now, I gave you guys two formulas, one's for the sample, one's for the population. They're essentially the same formula. It's just that one has little n, which represents the sample, and one has big N, which represents the population. The only other difference is the symbol that we use to identify that it's the mean. For a sample, we use X bar, and for a population, we use mu. Alright, so the mean is one measure of center. The median is another measure of center. The median is simply the middle number of your data set. It's probably one of the easiest things to find. Basically, all you have to do is put your numbers in increasing order and then identify what the middle number is. If your data set is odd, if the numbers in your data set are odd, then all you do is take that middle number and that's your median. But if it's even, you take the two middle numbers and then divide that by 2. Alright, so what's important about this? How do I know when to use the mean, and how do I know when to use the median? Well, the thing that's important is that you have to understand that the mean is influenced by extreme values. That means if you have outliers, if your data is skewed, the mean is going to be influenced by it. Now, the median, on the other hand, is not influenced by those extreme values. So we call the median resistant. It's resistant because those big values or those extra small values are not going to sway the median that much. Whereas with the mean, it would change the value greatly. Alright, so how can I use the mean and the median to describe my data? Well, if you know the mean and the median, and your data is skewed right, hold on one second. Alright, so if the data is skewed right, you'll notice that the mean is way bigger than the median. However, if your data is symmetric, well, the mean and the median will be just about the same. And if your data is skewed left, the mean is noticeably less than the median. So again, you can tell whether or not your data is skewed or symmetric just based off of your values for your mean and for your median. Alright, so when you're choosing your measure of center, generally you'll use your median if you have skewed data or if you have outliers, and you use the mean if your data is roughly symmetric. Alright, now we're moving into measures of spread. So the first measure of spread is probably the easiest to discuss. It's the range. And as most of you guys know, the range is just the largest value minus the smallest value. Now the range, we don't use it that much when we're analyzing data. It does give us some benefit or some usefulness, but typically when we're talking about the measures of spread, we do like standard deviation or variance. The range is just kind of like elementary. But either way, here's an example. It says compute the range of the data set. We have some temperatures in San Francisco and St. Louis. So if we're looking at the data set as a whole and we're not splitting it between San Francisco and St. Louis, we take the largest number, which is 79, and we'll subtract that from the smallest number, which I believe is 30. So here's 79, here's 30. And so if I subtract those, I should get 49. Alright, so my range will be 49 for the whole data set. Now, if we did it separately between the two, so if I wanted the range for San Francisco, we would find the largest value, which I believe is 63. I think that's the largest. And then we would subtract that from the smallest value, which I think, if I'm looking really quick, I think is 51. I subtract those two, and I get, 12. Alright, so my range for San Francisco would be 12. And similarly, if I do it just for St. Louis, my range for St. Louis again will be that 49. Alright, so moving on, we have what we call the variance. And we have two formulas. One's for the population variance, and on the next slide you'll see the formula for the sample variance. Now the population variance is basically just telling you how far your data is spread apart from the mean. All right. This is our formula for variance. It's basically the sum of your values in your data set minus the mean squared over the total number of observations. And so that's summarized a little bit more in detail on this next slide. Again, you find your mean, you take your mean, you subtract it from each observation, you square it, and then you sum those numbers and divide it by the number in your sample size. Basically what you're doing is you're finding the mean, you're subtracting it from the values, squaring it, and then you find the mean again. That will give you the variance, the population variance. Now, as I was saying, the other variance that we have is for our sample. It's essentially the same formula. The only difference is that we divide out by n minus 1. And the reason why we do that is it's a little bit complex, but the basic reason is to adjust for any variability in the fact that we're using a sample instead of the entire population. All right, so we have basically the same steps, except for at the very end, instead of dividing out by n, you're going to divide out by n minus 1. And again, we'll look at this in more detail in class. We'll actually calculate it out in class. All right, now generally, we don't use the variance that much. I mean, when you get into higher levels of statistics, you'll use it a little bit more often. But basically, the only reason why we even use the variance is to calculate the standard deviation. The standard deviation is really the value that we focus on. Because again, that standard deviation tells you how far your values are away from the mean. All right. And so for your sample standard deviation, you'll take that sample variance and you'll take the square root of it. And for your population standard deviation, you'll take your population variance and take the square root of that. All right, with that being said, we have something called the empirical rule. And basically, your empirical rule tells you how much data will be within 1, 2, and 3 standard deviations of your mean. So approximately 68% of your data will be within 1 standard deviation of your mean. 95% of the data, so a large amount of your data, almost all of it, will be within 2 standard deviations of the mean. And everything else, about 99.5% of your data, will be within 3 standard deviations of your mean. All right, now again, keep in mind this only works if your data is bell-shaped, if it's roughly symmetric. All right, so again, here's your little picture of your empirical rule. The bulk of your data will be within 1% of, 1 standard deviation of your mean. Then 95%, so almost all of it will be within 2 standard deviations of the mean, and then everything else will be pretty much within 3 standard deviations of your mean. And again, that works if it's bell-shaped. You don't have a whole bunch of outliers and all kinds of stuff like that. If it's roughly symmetric, this will work. Now we have another way of calculating, almost very similar to the empirical rule, is our Chebychevs inequality. And basically what that says is it's telling you the proportion of the data that will be within 1, 2, 3 standard deviations of your mean. And so the difference is it's a kind of more of a loose way of figuring out how much of your data will be within however many standard deviations from your mean. The empirical rule gives you a more accurate number, but this is just another way of figuring it out. So basically, all this is saying is that at least 3/4 or 75% of your data will be within 2 standard deviations. That's if I substitute 2 for K. And then 8/9 or 88.9% will be within 3 standard deviations of the mean. And it's saying at least. So it could be 88.9 or more, which, going back to the empirical rule, we know 95 should be within 3 standard deviations. So again, this one gives you a little bit more flexibility. It's a little bit more loose in terms of how much of your data should be within however many standard deviations, but it's just another way of analyzing your data. All right, so another measure of position is your Z-score, and it really goes right back to that whole empirical rule. is telling you specifically how many standard deviations something is from the mean. So your z-score, you basically take your value, your data value, subtract the mean, divide out by the standard deviation, and you get this number. And that number tells you how many standard deviations you are away from the mean. All right, so how does that apply to the empirical rule? Well, 68% of the data will be within one standard deviation of the mean, so your z-score would be between -1 and 1. 95% of your data will be between two standard deviations of your mean. So your z-score will be between -2 and 2, and then almost all of your data will be within 3 standard deviations of your mean. So you'll get -3 and 3. That generally means that your z-score is not going to be some large number. It's not going to be like 42, because that would be between 42. That would be 42 standard deviations above the mean. That's too high. Your z-score will typically be between 3 and -3, maybe a little bit higher, like 3.2 or something like that, but it's not going to be very large. All right, another way to identify position is what we call a percentile. I'm sure all of you guys have heard of percentiles before. It tells you your position or how well you did compared to everyone else. Basically, if you're in the Pth percentile, you did better than P% of the individuals in the study. All right, so here's a formula for calculating percentiles. This formula is a little jacked up. This should say L equals P over 100 times N. And with that formula, you'll be able to figure out exactly what percentile you are. Another way of calculating percentile is just to put your data in order, and then just find the value that represents whatever percent you're looking for. So like if you're looking for the 30th percentile, well then you would just put all your data in order, find what the 30th percent would be. So again, dividing it out by 100, and then just counting to that number. All right, next we have our quartiles. Our quartiles tell you the 25th percent, the 50th percentile, and the 75th percentile of your data. So for the first quartile, it's the half of the lower half of the data. It's half of that lower half. So once you split your data in half, it's half of the lower half. Your second quartile is the middle half. In other words, the second quartile is just your median. And then your third quartile is half of the upper half, or the 75th percentile. All right, with all of that put together, we have something that we call the 5-number summary. The 5-number summary gives you your median, your first quartile, your third quartile, and your min and your max. So in order, it would be the minimum, first quartile, median, third quartile, and maximum. And that's how it would actually play out if you were to put the numbers in increasing order. All right, so again, 5-number summary: minimum, first quartile, median, third quartile, and then maximum. Now, occasionally in a data set, you'll have an outlier. An outlier is a number that's very, very large or very, very small in comparison to the rest of the numbers in the data set. Sometimes you can actually take out an outlier in your data set if you feel like it was an outlier because of a mistake, like somebody just typed in the number wrong. But if it was a true outlier, like the temperature in the 50 states and the temperature in Alaska was way lower than everyone else, well, it probably is way lower, so I can't take that out because it is a true data value, and we have to actually use the outlier in our data set. So again, the outlier is something that's very, very large, very, very small in comparison to the rest of the values in the data set. Now, your interquartile range is found by subtracting your quartiles. So if you take your third quartile and subtract it from your first quartile, you get what we call the interquartile range. So similar to the regular range, like the highest from the lowest, the quartiles, or the interquartile range, you're doing it from Q3 to Q1. And basically all that's doing is giving you the range of the bulk of your data versus the range of the entire data set. You would use the range of the bulk of your data. Because again, if you have an outlier, you don't necessarily want to use that number to find the range. So I wouldn't use those higher numbers or those real lower numbers. I'm just going to use the numbers that represent the bulk of my data set, the middle 50% of my data. All right, so here's your steps for finding outliers based off of your IQR. So basically what you do is you figure out your IQR by doing Q3 minus Q1. And then what you do is you multiply that IQR times 1.5. All right, a lot of people call this the 1.5 IQR rule. So once you have 1.5 times your IQR, you'll take that number and you'll subtract it from your first quartile and add it to your third quartile. So again, I'm down here, I'm subtracting it from my first and I'm adding it to my third quartile. And basically what that tells you is your boundaries for whether or not, for your outliers. So whether or not something's an outlier. So you're going to get two values. You're going to get a small number, you're going to get a large number. And if anything falls outside of those two numbers, they are outliers. If it falls within, then it's good to go. It's a good value for your data set. So again, to figure out whether or not something's an outlier, you do 1.5 times the IQR, subtract it from Q1, add it to Q3, and if it falls outside of those two numbers, well then it's an outlier. Alright, so we said all of that to just be able to construct a box plot. And so your box plot, you're essentially using that 5-number summary in addition to your outliers to create a graphical representation of your numerical summaries. So what you do, you find your median, you find your first quartile, your third quartile, you find your min and your max. You draw lines from the min to Q1 and the Q3 to the max. You draw a box around Q1 and Q3, and then you throw a line through the median. All right, and again, I know I'm giving you guys a lot right now. I will definitely show you how to do this in class. All right, so once you actually get that box plot drawn out, you have a box in the middle and you should have two whiskers off to the side. Some people call this a box and whiskers plot. And it basically shows you those five numbers that we talked about before of our data set. So it's telling you your center, it's telling you your spread as far as IQR goes, and it's telling you your min and max, which will give you your range. Alright, so once you have your box plot, you can look at the shape, just like with a histogram or a dot plot or a stem leaf plot. You can look at the shape from the box plot. If the median is closer to the first quartile than the third quartile, then the data is skewed right. If the median is closer to the third quartile than to the first quartile, then that data is skewed left. And if the median is approximately in the middle, like halfway, directly halfway in the middle, then we say that's symmetric.